So we have this vector lab to do, and of course what you're seeing up here on screen, this right here is the way we write a rectangular vector. Okay, so this is a vector in rectangular coordinates. The R is not for rectangular. All right, it's just one of the many or a couple symbols that we use for a general position vector. This could be V for velocity, A for acceleration, F for force, and you would have components of those vectors, and the components are just the magnitudes in those directions. All right, that's just general rule about that. This magnitude equation here would simply be the Pythagorean version, which I'll just put in a two-dimensional version. You'd have those components of a vector, that's the 2D version. And so in Pythagorean's theorem, if you want to know the length of that vector, all right, the magnitude would just be the square root of the sum of the squares. Now that works in 2D, it works in 3D. That thinking works in as many dimensions as you want to mess with. We only do 2 and 3D vectors, 1, 2, and 3D, so that's just the basics there. So those are, and you notice those brackets, those large angle brackets, we have been using that particular thing in our Python labs, except it was parentheses. So in a coding environment where you're writing code, obviously we don't have a keyboard button for those brackets. Well, we have greater than, less than, but those are different. And so parentheses often work. On vector graphing calculators, often will do vector math, and depending on the calculator, it'll either be parentheses, would be where you put the rectangular coordinates, or the curly brackets. It just varies on the calculator. You'd have to look in your manual to see what's going on. So these questions, when plotting the endpoint of a vector in rectangular coordinates, what are you giving the vector graphically? I guess I need to do an edit on my website. Hope I remember that later. Okay, which is sad because I just cut and paste them from the old Word document, so it's been a misprint for a while. Sorry to shatter your visions of my perfection. All right. When you plot the endpoint of a vector in rectangular coordinates, what are you giving the vector graphically? So what am I asking for here? So if I had, an XY plane, and I was plotting the endpoint of a vector in rectangular coordinates, so I could, go at 1, 2, 3, 4, and here's an x coordinate. This would be Rx, and maybe 1, 2, 3, and this would be Ry. What am I giving the vector? Well, neither one of those things is the vector. This thing could be a vector, and the y could also be a vector, but when I put them together, like I do have up here, okay, then that means, I've created a new thing. I've specified something new. So what have I given? So when plotting the endpoint of a vector in rectangular coordinates, so this is the endpoint of the vector r, okay, which we would properly put an arrow on if it's a vector. What am I giving the vector graphically when I plot the endpoints? there's at least two things that I'm imputing to it when I plot that endpoint. Giving it a direction, and what else? Well, if I just plot the endpoint, I'm just putting a spot in the Cartesian plane, but it's a spot that coordinates 2 points. And if it's the endpoint of a vector, then it's the endpoint of an arrow that is pointing in a direction. That's the most obvious feature, is that it's pointing somewhere. It's specified there. And I could measure that in lots of ways, namely an angle. All right. Well, what else does this vector obtain when I plot that endpoint? Length. And in fact, when you do the vectors lab, the simulation lab, as I recall, when you can drag the endpoint around and it stretches or shrinks that vector. So you're actually be able to see and feel, so to speak, the making of the vector. And that's really the idea. Largely the simulation labs are more like pre-labs. They're set up for something else we do, or they're the lab that's replacing what would be very difficult, tedious to do in lab and soak up more time than it's worth. And a lot of our labs, classical labs, have that downfall, is that there's a lot of setup, a lot of opportunity for error. We still do them because that's the way science works. Science is littered with a whole bunch of trial and error before we finally get it right, experimentally, theoretically, methodologically. And so we don't want to rob you of the drama of science, but we don't have to maximize it either. All right. So that would be a way to talk about number one, and there might be another way that you think of. And honestly, I think it would be terrific if somebody had an alternate view that they either came up with right now and shared it with the class, or when you're writing your various summaries, like you have some novel way. That would be cool, because then after you've graduated, I can pretend that I thought of it and all that. Number two, which thing, the vector or its magnitude, is dependent on the other? Which thing, the vector or its magnitude, is dependent on the other? Any thoughts? So we only have two choices, really, right? Either the vector is dependent on its magnitude, or the magnitude is dependent on the vector. And so we could probably talk for a long time about which one of those is right, because the vector, when I plot endpoints of the vector, that's the moment at which it obtains a direction and magnitude. So in one sense, so what is dependent on what? I made it this long and I pointed it in this direction. Is the vector the thing following, or is the vector the thing that's driving? And so really when I plot something in the plane, I am describing the length and direction. So the way we're going to write this law is the vector is dependent on its magnitude. Now, I really think, especially in this case, that it's really debatable. I think it's a toss-up. Which one depends on the other, because it depends on the way you're thinking about it. Now, why is this important? Well, often in science, we want to simply make a definition when we know that things are related. It's obviously the direction and the magnitude of a vector is related to the way I specify its coordinates. And the way I specify coordinates determines how its features are. It's a two-way street. And so when it's a toss-up like that, it doesn't really matter which one you choose, because in science, models are not so much right or wrong, it's how they vary in their utility. It's how useful the model is. So we don't have models that are wrong, because they would, if it was wrong, it wouldn't make it to the game. Okay? It'd still be stuck out in the parking lot. They wouldn't let it in the stadium. All right? But if it has usefulness, then it will survive as a model. And the most effective models, or the most widely used models, are the ones that are the most useful in the doing of work. Yeah.
So what's the difference between a vector and a magnitude?
Well, the vector, what's written there, those two formulas,
Yeah.
the bracketed thing is the vector in rectangular coordinates. It is a way to specify in the Cartesian plane, or in this case, Cartesian 3 space, the endpoint of a position vector. If I go to those x, y, p, z positions,
Yeah.
which are lengths, if you project it down onto those axes, they are lengths on those axes, but none of them are the length of the vector. They're parts of the whole. All right? So that specifies, it's a way to specify, it's a great question, because it forces you to dig into what we mean by the symbols, which is often overlooked. And maybe when you go read the textbook version of vectors, it'll make a little bit more sense. They don't write it this way in our textbook. They use IJK hat for the direction vectors, which is another standard view. And then the magnitude is a measure. So this is a great question, because I could say that the vector, as it's defined in the first equation, is the way I specify its endpoint, and the magnitude is the way I measure the length of the vector from its origin to that endpoint. And in this case, its origin is the origin of the system. We'll have other vectors that are differences between vectors, and their origin isn't the system origin, it's one of the endpoints of the other vectors. All right, so good question. So I would say the vector specifies where it is, the magnitude measures what it is, measures its length. But neither one of these exhaustively specify the direction. The direction is implied by the rectangular coordinates, but it's not measured. We haven't measured the direction yet. We're about to. That's the second lab we'll do. So we have that. So I'm gonna give myself some space here. So write an identity statement for a vector and its magnitude. Okay. So the vector, I'm going to use big R. It's just easier to write than the little r. I might go back and change that later. But we tend to write them in lowercase for positions, and force and things like that will be uppercase. So that's the identity statement for the vector, and here would be an identity statement for the magnitude. Yay, so we've been around this block a few times, writing identity statements. Preserve the identity on the dependent quantity, so on the dependent quantity. So if we make the vector dependent, and let me be clear why. I want to make the vector dependent because I want to write a vector definition that is exhaustive of all the properties of a vector. Because the way I've written the position vector above in the bracketed with the top equation, it doesn't tell me about its measure or its direction. So, at the top of the page, I'm not going to scroll to it, but it says, it goes back to the despicable me villain vector, crimes with direction and magnitude and direction. Because that's the way a vector is defined. It's a quantity that has both magnitude and direction. So we could find that in any textbook, physics textbook, and even in algebra, pre-calc textbooks will specify that, okay? And so we'll assume that we already knew that or could look it up, but how do we justify that knowledge? Well, that's what we're going to do, is justify that. So preserve the identity on the dependent quantity, which I've written in green, with the quotient identity of the independent quantity. So this thing here. So if I put the magnitude of the vector there, so all I've done is preserve that identity. Okay? Identity preserved. Then rearrange the axiom to encode for the relationship between the dependent and independent quantities by means of a quotient relationship. So here's the subtlety here. Okay, we've gone through the motions of doing this process several times. We did it with the circle to obtain the constant pi as the relationship between circumference and diameter. We had a slightly better reason to make the diameter or the circumference dependent on diameter. We've done this maneuver for the zeroth laws. Those were really clear. Everything's dependent on time. That was a dead ringer. There was no doubt that position and speed are dependent on time and not the other way around. That was easy. With the area labs, mixed bag there of why we chose them to be that way. Now we're wanting to define, so we have the words that we could go find, vectors are quantities of magnitude and direction. I need to encode for that mathematically. And if that's the case, then that means vectors are dependent on their magnitude and direction. The way I write a vector needs to somehow be dependent on that, okay? And so that's where we're going. So we're going to put the vector so R, we're going to put that in quotient relationship with its magnitude. And let's see here. So now I have a new thing, this thing right here, vector per magnitude, a this per that. Okay? And the magnitude is going to have units of length in this case, since it's a position vector. If it were a velocity vector, it would have units of meters per second. But the vector has the same units. The XYZ part of the vector, that's also in meters. And so when I do this maneuver, I'm going to have compatible units that cancel out. All right? And so I now have a vector definition where, this is the vector. This is its magnitude. And this is some new thing. And if you think about that new thing, if you go back to your drawing where I had the right triangle and I had an X part and a Y part, what this is saying is I take this vector, and if I divide each one of the components by its magnitude, I'm basically getting that projection. I'm getting a measure of the angle. It's really a cosine. That's what it is. Every one of those ratios is going to end up being a cosine. I'm giving away part of the next lab. All right? But this middle thing is going to be a directional thing. And so now I have a mathematical statement where I have three parts. I have the vector itself equal to a product of its properties, its magnitude, and something that is akin to directions. Because one way to talk about a direction is an angle. An angle tells me, 90 degrees that way. That gives you a direction. It's a way to talk about direction. So So that last part answers number 6. And oops, I guess I can make that bigger. All right. So the next part of the lab, or part 2 of this lab, is this, what to call this new thing. And so that little symbol, R hat, the caret, the keyboard symbol caret over it, that is the way we identify the unit vector. So R with a caret symbol, we pronounce it R hat, we call that the unit vector. Now the interesting thing here, and I think I lament about it later on, is why is this a unit vector? Because I'm going to have meters divided by meters. Seems like I don't have no more units. All right, but that's what it's called. And I just work here. It was named that before I was born, so we'll have to just live with that. Consider, number 1 here, consider the properties of a vector and its magnitude that are now in a quotient relationship. In what ways are they the same and not the same? Well, I sort of just answered that. They're the same in the sense that they have the same units. They're the same in the sense that they're related to the vector itself. But they have the same units. That's really what it is. The other thing is that a vector is not its magnitude, and its magnitude is not the vector. One specifies the other, one measures the other. The vector specifies indirectly what the magnitude is going to be, and the magnitude is a measure of that specification. So it's another relatively simple set of distinctions. So this next part, rewrite the unit vector such that the relationship between a vector and its magnitude is now enclosed within the vector notation. In other words, put each element, the rectangular components of the vector, in quotient relationship with the vector magnitude. All right. So this would mean R hat would equal I'm going to go back to my, I'm going to use the big R, just like I said earlier. Let me fix that, because my little r's look like square root symbols. So R hat would be R Rx per the magnitude of R, Ry per the magnitude of R, and Rz per the magnitude of R. Be very careful that you recognize that the numerators in those fractions are magnitudes. They're not the vector itself. They are the length along those particular axes. And if you think about it, let's just take a look at this here. So, you know, what do the components in this strange new thing specify? And so if we so that's the length of R, and that's Rx. So what, these two line segments have something in common. They have this common endpoint. And this angle that's between them could be the angle, relative to the x-axis. And we have these ratios that I already said earlier what they are. So what trig ratio relates and adjacent to its hypotenuse? Cosine. So cosine of theta would be the adjacent over the hypotenuse. And that means this component would be the magnitude of the vector times cosine of theta. Guess what you learned in your trig or your pre-calc course? You learned how to do components of vectors. The x component of a vector, or the hypotenuse, would be the length times the cosine of angle between them. The sine would be the length of that vector times the sine of the angle between them, etc., etc. So going back to what you learned in the math course that was prereq to this one, you would have just started with those component definitions. The x component is r cosine theta, the y component is r y theta. If we had a z, which you didn't do in that one, it would be a little different. But in this one, we can make them all cosines. They'll all be cosines instead of sine, cosine, and whatever. So the unit vector, so my point here is the y part and the z part are all going to have the same feature. They're going to be related to a trigonometric, they are trigonometric relationships that specify an angle. So the x part of this vector is a cosine of an angle. And cosines are a ratio, sines are a ratio, tangents are a ratio. They're all ratios of sides. And vectors are sides of some sort of triangle. All right? So this new thing we created, the unit vector, is a pointer. It's an angle pointer thing. And it's a pure number. It's a set of pure numbers. Right? It's what gives a vector its direction, mathematically speaking. All right? So you could basically copy this triangle, and you'd have ry, and that would be a theta y. You'd have an rz, and that would be a theta z. So each one of these triangles could be positioned in 3 space relative to a 3D axis. Okay, that's hard to draw. All right, so I'll find a nice pretty picture of that and probably add it in here later. But the idea is this first one will be the same. So literally, the difference between this triangle and the next two is the labels, and you might be standing it up on its end and sweeping out from, say, the y-axis vertically, and flatten it out in the z-plane and sweeping it out from the z-axis. So they'll look the same, just it's how are you looking top down, face on, just what axis are they relative to. All right. So let's see here. Well, this works pretty darn good. I have not made a video using this toy, this app and this toy, while using the browser inset. So, yay. I just need to make sure that on my activities I leave white space next to everything, because that worked out pretty good. All right. Number 3. part 3 of this lab. Given your final axiom from there, so let's imagine what that axiom might look like. So I would have R equals a magnitude times a direction, or vice versa. You could have R hat, R mag. You know that it doesn't matter which order you multiply. We tend to write it this way. All right, and when there's a couple of labs we'll do in Python where we write it this way because it's the standard way to write it, and and you'll notice this even in your calculators. If you put a vector in, usually there's a function that's usually called ABS for absolute value, and an absolute value doubles as magnitude. But where in Python we call it mag. Makes sense. Mag a vector, and it'll do the Pythagorean identity for me. The unit vector is a thing called norm. Perpendicular, it normalizes it. And so the norm of the vector is those 3 numbers that basically are going to be a cosine set of cosine decimals, if you will. And on your calculators, I think they call it unit. It's been a while since I've used a calculator to do that. Okay, I'm using other things when I do that. Or I just convert it from rectangular to polar, and it tells me the angle, which is useful as well. So that's what it looks like, but this, in one sense I could have, and I'm just going to use a 2-dimensional since I'm running out of space. So that's the magnitude of the vector, and then the pointy thing would be Rx over R, Ry over R, and this, so we'll scooch down here. I'll go back to the magnitude notation because it's simpler, but this is going to be the cosine of theta relative to x and the cosine of theta relative to y. And so our vector, okay, has magnitude and direction. So what we've done is go from the words that we could have looked up anywhere, all right, and we've told the backstory. If I just take the representations that come with that territory and try to make sense of them, I can actually justify this definition that vectors are quantities that have magnitude and direction. But they have magnitude and direction because of the way I impose a measurement system on them. It's not like there's such a thing as vectors in the real world. Vectors are things that they're a model. It's just a model. And we use it quite effectively to make predictions and various measurements. So this question here, come up with a way to explain how a series of numbers without units specifies vector's direction. Well, it's because they're cosines. That's what they do. They specify a direction because they are the cosine of an angle. And an angle is a directional thing. So we get at direction indirectly because of the features of a rectangular coordinate system. You're basically guaranteed some right triangle opportunities. And if you have right triangle opportunities, guess what you have? You have magnitude and direction. How convenient. Right? So, but it is. It's really handy. Now, this one here, I'm still bugged by this, but I'm not in charge yet. So, why do we call this strange relationship the unit vector when it has no units? And I ask this question, or does it have units? So let's think about this for a minute. Look up at the this Rx per R. R sub x would be a length along the x-axis. The magnitude of R is a length. And assuming they're in the same units, which would be easy to do, if I take some number of meters and divide it by some other number of meters, I no longer have any meters. In fact, if I say R sub x per R sub x is, in one sense, a part of the vector. In fact, it is. Each component is a part of the vector. All right? And the magnitude is, in one sense, the whole. It's the whole length of the vector. These are weird parts because they don't add up. You know, if I took a 3 meter x component and a 4 meter y component, their magnitude isn't 7. Their magnitude's 5, isn't it? So they add up in a very weird Pythagorean way. So the sum of the parts is the whole, but the parts are constrained in a weird way. They're constrained by a right triangle. Okay? Now, what I didn't put on here, but it's part of your simulation lab, all right? And we'll probably try to update that. To our show here, so I'll go back. All right, the range equation. So, kind of done with vectors for the moment, and we want to get into projectile motion. So we've done one-dimensional motion that we apply the zeroth laws to. So one-dimensional kinematics, and now we have 2 or 3-dimensional kinematics would be what a projectile is. So imagine a football being kicked from ground level, or a cannon firing, or throwing a football. These are projectiles, things that are tossed, thrown, lobbed, fired, etc. from ground level, or above ground level, or below ground level, and they land at ground level or anywhere that you want to. Okay, so let's jump in here. So horizontal distance. When we talk about the range, we are talking about the horizontal along the ground distance as if the ground were perfectly flat. Now the reality of our problem may not be exactly that way. You might be firing from a valley on top of a cliff, or from a cliff down into the valley, or maybe you're kicking a football from ground level and it hits the goalpost, the crossbar, or lands in the stadium above ground level. But there's still a horizontal range. If I were to lay a ruler on the world, it started here at ground level, and then over here it landed above ground level, but if I drop a line down, this is how far it went horizontally. So range is always a horizontal distance, an x part of motion, if you will, because we typically use the x-axis to indicate horizontal motion, and the y-axis for vertical motion, and z would be in and out of that plane. So choose a symbol for the distance quantity called range. Anybody want to venture what the symbol for range is? Well, what would be a nice letter to choose for range? Even if someone were to bold face the letter. Capital R. All right? So this is one of those times where we pick a letter that makes sense for the word that's going with it. Every textbook I've ever seen, the range as a formula is written that way. Okay, so we have that. Now, modify the first zeroth law in terms that make sense for this part of the projectile's motion at the time it starts its motion. So, first zeroth law that we've written, delta S equals V delta T. How could we modify the first zeroth law to be specific to the horizontal motion? Well, if it's a horizontal distance along a straight line, it is a displacement, and that change in position would be the change in position along the horizontal. So we could just call that displacement R. If you could imagine, an object following an arced path, so an XY parabolic motion, like a kick in a ball, all right? So let's say that object, had a laser pointer that hung out of the bottom of it and always pointed straight down to the ground, perpendicular, okay? And so that you could see how fast it's moving, like it was you could watch it on a line, okay? What speed would we be talking about if we were following that dot? Positions have components. Do speeds have components? How is the speed of a projectile? Just think of a ball being kicked, soccer ball, football. Does it have a speed in the x direction? Does it have a speed in the y direction? How is its speed in the y direction changing? We're getting down to some of the other questions. Well, initially it has no speed, right? Well, when you first kick it, it's going a direction. And it would keep going that straight direction if it weren't for what? Gravity. So part of its motion could be measured horizontally, couldn't it? So imagine that this weird football has a laser pointer that's pointing down along the y direction on the x-axis. And let's imagine that it has a pointer pointing horizontally at the y-axis. So I could watch two dots. I could watch an x-dimension dot and a y-dimension dot. So that y-dimension dot, speeds are going to either be constant or they're going to be changing. What's happening to the y speed of this object? It's changing. It goes from 0 to something, right? What does it do? What happens to the y speed? It starts at 0. Does it go back to 0? How many times does it go to 0? It's more than once. So let's just think of something going straight up. This pin that I'm tossing that no one can see on the video, so you'll have to pretend if you're watching this out in YouTube land. Before I toss it, it has 0 speed. It went to a maximum height. And at that max height, what was its speed? For a very brief moment in time, it had a 0 speed, and then when it comes back down, 0. So in the y direction, I have a changing speed that oscillates between 0 and 0. It goes from 0 to some max speed, and then it goes back down. And gravity is the reason why its speed is changing in that direction. Air is part of the puzzle, but it's a really super duper small part of the puzzle. We'd have to give this thing some wings or flaps to have air be a meaningful imposition on its speed. All right? So, in the x direction, that dot, is that dot speeding up or slowing down? Or is it staying constant? Stays constant. Why does it stay constant? Because the book said so. It does say so. Why does it stay constant? Well, you get to ask the question, so we know why the y speed was changing is because gravity is decelerating it on the way up and accelerating it on the way down. Is gravity working sideways? No. In fact, there's nothing in the way but air was in the way on the vertical, so I can just drop that. There's nothing causing it to accelerate up or down, or increasing or decreasing acceleration along the horizontal. So it's going a constant speed on the horizontal. And that dot that's moving along the x-axis would have an x speed, an x velocity, if you will. And time has no other component. So I sort of got ahead of myself there. So all that yapping answered these questions. We sort of did that already before I wrote the equation. Critical times in the motion of a projectile, those are going to be the starting and ending points. Of course, the critical times in the motion of anything will always include beginning and end, but for a projectile, at the peak height. Because at the peak height, I get a maximum in the y direction. Okay? It's also going to be half the range if it's ground level to ground level flight. Okay, so that'll come from your reading. Which horizontal speeds are the same? Well, all of them, as we determined. So at this point, we can't think of anything besides air that gets in the way of the horizontal motion. But air was also in the way of the vertical motion. But gravity was the thing that was causing the speed to change. Okay? Technically, air drag is always diminishing your speed. But, you've watched, movies where somebody jumps out of the back of, off a semi-truck into the back of some other truck or into the window of a car or something impossible, in normal life. Nobody does this. And why is that? You'd think that, if I jump off the back of a moving thing and try to jump on something else, I'll miss it. Well, no, because you have the same speed as the car. So the stunt people, they have the same speed as the vehicle they're jumping off of. So the only way they would miss the thing next to it is if they jumped behind it, then they would hit behind the car on the ground, and that would hurt. If they aimed in front of it, then they'd get hit by the car. But if they just jump straight over, then they land over. Same thing you could do. I'm not willing to try it, even though I know that it should work, is you should be able to jump up straight. If you could jump straight up in the back of a truck, you'd land straight back down. But in your mind, you're thinking, surely the car's going to go out from underneath me, and that would be bad. Yeah, it would, because you would still be moving at, whatever the car speed was, and you would have a nasty tumble, all right? But there's some videos, I'll have to find one where they actually do it. They have a cart with a little cannon, and the cart's moving, and you can fire that cannon, and that ball goes up, and it goes right back into the cannon. I'm still not going to jump out of the truck. I'm not going to do it. I need a lot of money, and I want to be in one of those big beach ball things. So that it'll be hard to jump, though, I guess. So number 7. given these findings, okay, we can expand this equation a little bit. All right, let's
Yeah.
continue here. I think I'm gonna go to a new screen here. So there's a couple of things. So we need to expand our equation. So I think you'll find it interesting that we're going to go from well, let me be careful here. So the initial speed of this projectile, okay, is going to be its initial speed in the x direction, all right? And so what that's going to mean, and you can just add a little bit of notation to the equation that we started earlier. But up there at number 2, this would be the most specific thing about the range, because since the horizontal speed is one speed, and it's the initial speed in the x direction, the most notationally exhaustive version of that speed, instead of just v sub x t, it's actually the initial speed in the x direction times the time of flight. Okay? And so v naught sub x, I could have vx, but it is one speed. So as long as you recognize that it's initial speed, that's fine. I'm also trying to get to the classical equation. And if I left it vx, we'd have to deduce that that was the initial x speed. So if its speed's the same at all points after it initially gets moving, then it's the initial speed. That's a more specific version of that speed, all right? So we have that piece of the puzzle. We forgot to answer the question, number 3, I skipped it, all right? What does the time variable represent? What is t for this projectile? So if we think about the x dot moving, what was that being projected down by? That fictitious laser pointer that was stuck in the projectile that was flying. So it's the time of flight. All right, so this is the time of flight. So that's an answer to number 3. And so number 4, we did answer verbally. What are the critical times in the motion of the projectile? Well, the critical points always include the beginning and end of some change. And often there's at least one point in the middle that's going to be a critical point. And if you think back to mathematics, often critical points represented where something was 0. Often means where something turned around. And so we have a 0 point at the peak height, and if it's a perfect range, meaning it goes from ground level back to ground level, you're going to have a perfect arc, and the peak height is also going to be at half the time of flight. It's also going to be half the range. Okay? Just perfect flight. All right? And you could go out and film that. Go to the park, film somebody kicking a ball, and you'll see this perfect arc if you were to frame by frame it, plot out the dots. Okay? So, some things we could write for number 4. So this is, 2, 3, and number 4. We could say beginning, middle, end would be those critical times. and you could say range equals 0 at time 0. That's an obvious. And we would have half range at 1/2 t time of flight, because this is peak height. So height, that's one of those EI words, right? Or is it an IE? I before E, except after C, or when followed by Y, or when sounding like A, as in neighbor or way, and all through the month of May and on weekends and holidays, because you'll always be wrong, no matter what you say. That's how it works. That's EI words. So height. Is that right? Did I screw it up? Is that the right way? Now is everybody confused about how to spell height? Yeah. Anyways, height, whether it's EI or IE. Oh, it's EI? See, I told you. EI. Yeah. Height. For this lecture, it'll be an IE word. All right, I love it. I guess the range would be itself at t equals t. That's sort of a no-brainer. I'm not going to write that. All right, number 5. We already answered 5. In fact, this is the answer to 5 as well. Actually, I guess I should say that's the answer to 2. All right, so we didn't write all of that out in the other one. It was just spoken, so I wanted to go back. So let's think about number 6. Which vertical speeds are the same? Well, the initial speed in the y direction has a magnitude. And that's going to be equal to the final speed in the y direction magnitude. Why aren't they equal, perfectly equal? Why isn't the initial y speed of a projectile perfectly equal to the final y speed of a projectile? Vector, think vector. I just told you their magnitudes are the same. What's not the same? The direction. That's why I can't, if I just wrote v naught y equals vy, without the arrows, that actually is okay. Because if I don't put an arrow over it, I can't claim it's a vector. So one of the assumptions that you'll read about is that if you leave the arrow off and or it's not bolded, then it ain't a vector, it's its magnitude. So I am going to write vy equals v naught y. But I wanted to say that because you want to be mindful that the up speed is the same as the down speed, but not to confuse that with the up velocity is the same as the down velocity. That would be incorrect, because velocity specifies a direction. Speed does not specify a direction. So if you mean speed over here, you're absolutely right. They are the same speed. One's up, one's down. Okay? Just, it's easy to lose sight of those particulars in vector land, so don't want to do that. So the range, okay, when time is half the time of flight, I'll put t1/2 for half time of flight, is going to be 1/2 of the range as a function of time, which is what I have up here. Okay, that is range as a function of time. We didn't write it r per and t, but it is. R equals something, and the parameter is t, so it's a function of time. So we have that. When, let me switch colors here. when Vy equals 0. Okay? In the up direction. So at the first time, the first time I hit speed in the y direction is 0, the range is half of what it's going to be. The range at that point is half of the range. That's our thing there. So need more space. Now number 7. Here's some things that aren't going to be obvious because we haven't used the expansion of the second zeroth law in this way yet. All right? So let's write the second zeroth law is A delta t. So we have this going for us. I can write this as V equals V naught plus A delta t. And so what this can go to, if I want to specify direction, so I could have V in the y direction, okay? So I'll transform the general into a specific. That means that the initial speed is also in the y direction. I can't have two directions at the same time in an equation, all right? Unless I'm doing vector equations. Now, here's the thing. If I'm going in the y direction, acceleration has a particular value, okay? And it's down. Its direction is negative, all right? So what you'll find in every textbook in this galaxy is minus gt. All right, so I'm swerving from the way we developed the second zeroth law, turning it into a particular direction speed equation like you'll find in the textbook. Okay? So we developed the backstory for everything that's in your textbook, and we'll continue to do that. All right? But often you'll need to look at textbook solutions to be successful in certain computations. All right? But you don't always have to. Sometimes you can get away with it the way we did it. It just varies. So here's this way to look at it. The final speed in the y direction consists of the initial speed that you start with in the y direction minus the acceleration due to gravity times time. But realize, and this is the importance of the backstory, these things here go together. This is a change in speed in the y direction. A delta t, or in the particular case of free fall of a projectile minus gt, or g delta t, that is the change in speed of the object. So guess what? The final speed is always going to be your initial speed plus whatever the change in speed is. And what we've done with our change variable is it's specified in time. So this is actually v as a function of time. Now we didn't write v parent t, all right? But if time's the independent variable, then that's what the function is in. It's in time, period. All right? We don't need to write all that notation. It gets cumbersome to keep writing that all of the time, but in our heads we need to know that that's the case. All right? So there's that. Now I'm going to just kind of separate that, and I'm going to rewrite this equation because I want to make a different point. All right? The final speed in the y direction is necessarily the opposite of the initial speed in the y direction, or velocity in that case. All right? I have a positive speed up and a negative speed down. or the final speed down is the opposite of the initial speed up. All right? So sometimes math has to turn our thinking around. It's just the way math is. Sorry. It's a troublemaker. All right? So we have this. And so developing the range equation, there's a couple of ways we do it. I have videos and stuff on it that you'll want to watch and then get to the problems. This is the simpler way mathematically. But conceptually, I think it's harder than the other derivations. And so there's this give and take. There's multiple ways to look at it, and that's how you become a deep learner of things, but having multiple ways to do that. Well, guess what this does for me? I'll spare you all the algebra. This means that time, I can just pull time out, all right? And it's going to be 2 v naught in the y direction over g. I can get away with that murder. Which means I can go back to my range equation, which was range equals the initial speed in the x direction times time, but now I've rewritten time as 2 v naught in the y direction over g. Now, there's a reason why this is important, and I've never read it in a textbook. Well, the math I'm doing here shows up in pretty much every textbook. But the reasons, I've not read good reasons to do it other than math lets you get away with it. Okay? Here's why this is a good reason. Taking advantage of the speed equation so that range is no longer a time-dependent function gives me an advantage, but it also allows me to specify range in terms of both parts of the object speed. I now have an axiom that puts these elements, I can rewrite them, 2 v naught x, v naught y over g. Because guess what every projectile has? Its initial velocity vector is comprised of at least 2 parts. Every projectile has at least 2, an x and a y part, and a z part too. The z might be 0 if it's just staying in a perfectly straight line, which you can always imagine it to be that way, even depends on your system. So I have this nifty thing here, but I still have these initial speeds, and I may not know what the components are. But guess what I could do? If I had a radar gun, I could go, initial speed was of the ball. So they don't typically do that in football, but like if you watch tennis, they know the serving speed. Baseball, they know the pitching speed. Why is that? There's basically a radar gun, fancy motion detector like we'll end up using here probably next week in lab, that's measuring the distance in time, and it gives you a speed. Okay, so I could do that on a football field. It doesn't matter. They don't care about that in football, all right, or soccer. They don't care about the speed of the kick ever, just how far it goes. They're concerned with the range in a football game, right? So I'm going to give myself some extra space here to wrap this up, such as, now I have the advantage of a range equations that is specified in terms of its parts of motion. All right, so range, the last thing I wrote, I think, was 2 times x speed times y speed over g. So let's think for a minute. Now, at this point, if you just said, well, I remember that the x part of any vector quantity will be that quantity times the cosine of the angle. That's just applying a definition that's in every math book, and it's also in your physics book. All right? And V naught y would be V naught sine theta. So that means that my range equation could be written as 2 V naught cosine theta, V naught sine theta, all over G. Which means my range equation could be written as V naught squared over G times 2 sine theta cosine theta. Does anybody recall what that simplifies to from their trig course? There's an identity. Remember you were told to never forget them? And that if you did forget them, people would come to your house and say mean things to you. If you but there is a simplification of this, and that trig identity is written as the sine of 2 theta. All right, I have that double angle. So the classical range equation is that one. Every textbook has that in it. Every textbook essentially goes through the same mathematical maneuver that I just did, okay? But doesn't give the reasons. It just, here's the math, you can do it. You get a simpler equation out of this. The important thing to get from this, something that you could conceivably put in your learning outcomes essays and those sorts of things, is why we would do, and the advantage that comes by finishing the math is now the initial speed. This is the magnitude of V naught squared, okay? Mag of V naught squared. So if you know the initial speed, meaning how fast it's going, the direction doesn't matter because that's accounted for in the angle. So all of these projectile problems, if a kicker punts, kicks the ball at 40 meters per second from an angle of 55 degrees, what's its range? Well, you put, the 40 meters per second and the 55 degrees, crunch it in the formula, you know how far it's going to go. Okay. It actually won't go that far because air drag will shorten its range. But it'll go close. All right. There's always that going for it. But that's the range equation. That's how it's developed classically. I have a different way of getting that is showed in the other videos. Is how we add vectors graphically. And so if I have some vector A and some other vector B, the way that I add them graphically is if I go from the tail of the first one to the tip of the last one and draw a straight line, that's the sum of those two vectors. So this would be A plus B. Now, these are all vectors, so I'll go back and be proper in my notation. But when the sum of the parts equals the whole, this isn't arithmetic. We're not in Kansas anymore, Dorothy, all right? This is different. This is weird. This requires a different way of looking at sum of the parts equals the whole, all right? And this vector, A and B, would have their A sub x and A sub y components. B would have B sub x and B sub y components, and A plus B would be the sum of the x components, comma, the sum of the y components. That's how you go through those motions, and your simulation lab will show you that. So you'll go through those motions and go, okay, I believe. I mean, but for now, you know, if you need to, you can draw a button and label it, I believe, you know, and press it. You could just press that button and it'll work out. I need to like have Office Max make me. Who has that easy button? Is it Office Max on the commercials? Or the big red button? Easy. I need to get an I believe button, hand them out, buy it in the bookstore. What do you mean I have to pay $50 for this? What do you mean Van Gilder's getting 45 of it? All right, so I need to do that. That'd be great. I need to get my Harley finally. All right. So graphical addition of vectors works that way. It would not matter how many there were. We could have this plus that plus this plus that, and it would still be the case if I go from the tail of the first one to the tip of the last one. This will be A plus B plus C plus D. And so, remember I was talking about how we have displacement versus distance? So the individual vectors, the zigzagging in white, that's the distance of the path. That's the path length. The green vector, the sum of those path lengths, the sum of those vector displacements is the overall displacement from position, say, 1 to position 2. The displacement of the entire path length is less than the path length in this case. So I could treat each individual path length as a vector if I put it in the same coordinate system. All right, so this, it's like if you on your map, like you're doing a mapping to some place you haven't been yet or don't remember, obviously you can't go in a straight line because your car doesn't fly, all right, unless it just happens to be down the street. So you have to zigzag your way, so while it's true, I live like 7 miles from here, but it's a 10-mile drive or something like that, whatever the McCartney zig and the Overfield zag is, plus whatever else I have to zigzag. It's not just straight line distance. So the maps, your Google Maps or your Apple Maps or whatever maps you're using, they are giving you the displacement, the true vector displacement. It depends on how you're using the map, because your map will give you the miles of the path length, but I've seen some maps that tell you how far away it is. My Apple Map doesn't do that, and I don't think Google does either. But if you're looking at a map, anybody travel for a company yet? Well, you will. And if you travel for the government gives you straight line distance, mileage. Okay? When I travel for the school, like I take a trip up to ASU or something, I get the straight line distance mileage. Everybody has their different ways of handling that. Anyways, so that's how the vector goes. All right, let's go back to